second half of the aspirin synthesis. So all of you, or most of you, I think, are at the point where you have your salicylic acid. So we're going to take the salicylic acid now and convert it into aspirin, which is just acetyl salicylic acid. So basically what we're going to be doing is, we hydrolyzed the ester originally, right? There used to be the methyl ester here. So we hydrolyzed that in the first half of the synthesis. The second half of the synthesis, we're putting on an ester again. It's just not at the same place. So we are going to take the phenol of the salicylic acid and put on a 2-carbon ester group on it, what is called an acetyl group. All right. So just kind of a FYI. I'm sure you're all very familiar with aspirin by this point in your life. So aspirin has been around for quite some time, really since the ancient Greeks. And of course, they didn't really know they were taking aspirin, but they would take the bark of the willow tree and make a tea out of it, and they recognized that had like anti-inflammatory properties and helped with aches and pains and things like that. So what they were doing is they were extracting something that's called salicin out of the willow bark. And so back in the late 1800s, a very young Bayer pharmaceutical at that time was starting to try to figure out what it was that was in this substance that gave the anti-inflammatory properties. And so they started working actually with, started selling salicylic acid as their original anti-inflammatory. But salicylic acid had some other not desirable qualities. It really upset people's stomach and things like that. And so what Bayer then did was, instead of selling the salicylic acid straight, they started selling this acetyl salicylic acid. And you can see there's a pretty significant difference in the acidities of those carboxylic acid compounds. And it really helped with mitigating the negative side effects that the salicylic acid had. Now, in the body, once you take aspirin, once it gets into your blood, it actually gets converted back into the salicylic acid. The salicylic acid is the anti-inflammatory agent. But this approach is very common in drug design. It's what we call a prodrug. So you take some kind of a compound, and as that's not the active ingredient, and then once in the body, it gets metabolized to the active form. And there's a whole bunch of reasons why drug companies do this. It could be that maybe the active ingredient is not well absorbed. It could be that, like in the case of aspirin, where the active ingredient causes some undesirable side effects. Especially if you're dealing with drugs that have to get into the brain. There's a very discretionary layer that really restricts things from getting into the brain. It's called the blood-brain barrier. And so those drugs have to be very specially designed, because only certain things can permeate the blood-brain barrier. And so, but there's a whole host of reasons why drug companies do this, this kind of pro-drug strategy. I'll show you a newer, more modern version. This is tenofovir, which was developed by Gilead Pharmaceuticals in South San Francisco. This is one of the most common anti-HIV agents on the market. And you can see that this is the way the drug is sold. You've got these big kind of groups hanging off the phosphonate. But once in the gut enzymes end up hydrolyzing all of that to this. And so this, all of that weird phosphonate ester stuff, that just helps to make the drug, it does a couple of things, but most notably it helps with the absorption of the drug. And so, but yeah, this is a very, very common approach in drug design, this pro-drug strategy. But in any case, let's move down to the chemistry of the day. What you're going to be doing is you're going to take the salicylic acid and you're going to react it with acetic anhydride. And so this is a reaction that we saw back in the derivatives, back in Unit 3. You're just taking an alcohol and reacting it with an anhydride. And so that should give you an ester. Right? And so we already looked at the mechanism of this back when we were doing the derivatives chapter, but there it is briefly. The way you're going to do this, it's very quick reaction. You're going to take around, well, I'll tell you what, you can use as much of your product as you want. The lab manual procedure says to use 0.42 grams of the salicylic acid. You have a lot more than that. So if you want to use more of your product, you can. You will just need to scale it up appropriately, you know? So it says, the lab manual says to use 0.96 mils of acetic anhydride. If you're going to use more of this, you need to use more of that, right? In a quantitative manner. You know, if you're going to double the amount of salicylic acid, then you need to double the amount of acetic anhydride. Okay, so I'll leave that up to you. You can either do it as written in the lab manual. If you want to kind of go big, you can increase your stuff proportionally. But in any case, once you get that mixed together, you're going to use a couple drops of phosphoric acid. This is just going to catalyze the reaction, make it go a little faster. It is a very quick reaction. It should be done in around 10 minutes. You will need to heat it, but monitor the temperature. You're not refluxing here. You're just going to heat it to, I'd say between 50 and 60 degrees. If you heat it too much, you will actually cause the reaction to reverse and you will hydrolyze the ester again. So keep an eye on the water bath. You do not need to run water through the condenser for this because you're only heating it to 50 or 60 degrees. Okay, so you can essentially just use an air-cooled condenser in this setup. What you're going to do at the end of the 10 minutes is you can let the reaction mixture cool a bit, and then you're going to add a few mils of ice water to it. You will probably need to scratch this with the glass stirring rod to get it to precipitate. Sometimes it doesn't precipitate well. So you might have to work at it a little bit to get it out of solution. You might have to put it in an ice bath for a little bit and scratch at it in the ice bath. Okay, you might have to add a little bit more water. So you're going to have to play around with it to get it to come out of solution sometimes. In the end, you are going to be recrystallizing from 50-50 ethanol water. Okay? And this is going to depend on how much you have and as far as how you do this recrystallization. If you do the lab manual method, you're not going to have a whole bunch of product. So it's not like you're not going to recrystallize it in the same way that you did the salicylic acid, let's say. Because with a salicylic acid, you were starting with like 3.5 grams or something like that. Here you're starting with 1/10 of that. Right? So you're going to have to adjust the way you do things accordingly. So if you do use the small amount that's written in the lab manual procedure, you're going to want to, the way I would probably approach it is I would probably take and put it in maybe a test tube. So take the crude aspirin, put it in one of your test tubes, get a second, maybe a small beaker or even a small test tube, something, with a little bit of your ethanol water. You would, have that on the hot plate. Get it very hot. You might have a second beaker with hot water if you're using the test tube. that'll just be the water bath. You'll add you're probably not going to need very much. You know, just you want to remember when you're doing the recrystallizations, you want to use the bare minimum of solvent possible. Just take a little bit of the hot ethanol water and put it in there, and then you can take and place that in the hot water bath. Get it as hot as you can, and just kind of shake the test tube every so often, trying to get all of that aspirin dissolved in the hot ethanol water. And then once you get it all dissolved, take it out, let it cool at room temperature, and hopefully you'll see the crystals form. And then you'll just vacuum filter those. I would not recommend characterizing your crystallized aspirin today, because it's still going to be very wet coming out of the ethanol water, which is fine. You'll have plenty of time on Monday. You can just start with the characterization of the aspirin then. Okay? Any questions on the procedure or what we're doing today?
Just have a quick question. I still have to separate out my salicylic acid. Will I have to dry that in the oven before doing part B?
Yeah, I probably would, just to be safe. Yeah, you don't have to leave it in there for very long, but just let it sit in there for a few minutes while you get everything prepared for your for the next part. I mean, mostly just because you don't want to characterize wet product. So, okay, any other questions? All right, well, the good news is our printer is working again, so you'll actually be able to print your spectra. Yeah, that's really all I got to tell you.